Hey guys, welcome back to AlgoYogi, and we are doing tree series right now. So let's move on to our next problem, which is construct binary tree from in order and post order traversal. Let's visit the problem on LeetCode, and the description is really simple, which is given two integer arrays, in order and post order, where in order is the in-order traversal of the binary tree and post-order is the post-order traversal of the same binary tree. Now we have to construct the binary tree and return the root node. So let's understand how we are going to approach this problem. The description is quite simple. Now it's just how we're going to make use of in-order array, which is for first example is this, and post order for the same example, for the same tree is this. Also, one thing that they have mentioned in the constraint is like all the values of this tree that we are trying to create from in order and post order traversal they're all unique. Okay, so you won't see any two nodes with a value 9 or 3 or whatever. They're all unique. Now we know that when we follow in order, the way we visit nodes are basically left, and then we visit root, and then we visit right subtree. Okay, so now, and then post order is basically first you visit, so it's post. So let me tell you a simple trick to remember in order, post order, and pre-order traversal, which is if it is in order, root is in the middle, left and right remains on the end, and then post order is basically you bring root basically in the end, and then it's left, right, root, and pre-order its root is in the beginning. So it's going to be left, right, and root. Now tell me, when we look at post-order traversal, then we will actually visit the root right in the end. So if we are visiting root right in the end, that means what? That our main root, basically the root value is basically at the last index, which is over here. This is our root value. So if I tell you, in order to construct the binary tree using post order and in order, I will simply first pop the value from my post order and make the node out of it, and then I look for that value in my in order. I find that index, I find the index of 3 in order, then I know that in order traversal, this value which I just made root over here, that will be right in the middle, and the left side of this will be basically left subtree, and right side of it would be right subtree. So now this subarray will be basically, we will be using it to make the right subtree of this root 3 and the left subtree of 3, and then the remaining subarray would be used to make the right subtree. That's quite simple. So basically this side we will have 9, and this side we will have 15, 20, and 7. Now these, we haven't created them yet, but just like we have created this root and assigned what is going to be in the left and right of this subtree, can't we just call that same recursive function on this array and this array, given we provide this post order to basically both of them. So now post order is only used for popping out the root. So now let's say I will pop out 20. I will pop out 20, and the reason I'm popping out 20 is because in my post order, when I'm popping it out, that means what? I have to basically, if I'm visiting the post order traversal, then it's like what I had to do is left and right subtree, and we need to construct basically right subtree first, because we are popping out the roots from post order, so that it visits right subtree in the end, so that we just need to create right subtree first and then come back to left subtree, and that we can simply keep breaking things using this in-order traversal. Also, one more thing is basically to get the time complexity of big of n, we need to store these value and their indexes in a dictionary, so that we can simply look up these indexes in big of n, big of one time, so constant time. So okay, let's implement the solution now. Let's go to our code editor. It's really simple. I think the code will make it quite simple. Okay, let's write down our code. So we're going to have a dictionary. Basically, let's call it in order indexes. Let's call it index, and then it's going to be basically node, and then its index in for I and node in enumerate what we are enumerating in order. Okay, awesome. Now we're going to have a DFS function that's going to take left and right pointer, and if left is basically greater than right, then it's basically the base case. It means we have already covered all the nodes going in order. So these pointers are basically they represent two end of the array, that whatever subtree we are processing, initially it will be the entire in order, which is like it contains all the value of our binary tree, and then we're going to keep breaking it. So these pointers will keep shifting, like we will shift these pointers wherever we find that index in order, and decide to like create the left subtree and the right subtree, basically while popping the values from the post order. When we pop, so we have to create the right subtree first, because that's how the values are ordered. They're in post order, they're left, right, and root. Okay, so we're gonna just return none from here, and then here let's basically create the root node. Root node is basically tree node, and we are popping the value from post order. So post order dot pop. Awesome. So popping this value. Now we want to find the index, and index would be basically in order index, and that is the index in order, where we want to break it into left and right subtree for this particular root. So here we're just simply finding it using root.val. Okay, so now we have the index. Now we're going to simply root.right. That's what I said. We want to assign the right subtree its values first. And that would be just calling DFS on. So for right subtree, the right pointer will remain same, but it's just the left pointer will shift one index up from middle index, because we are already using index right here. So, and that will be right. All right, and let's do the left. That is also, sorry, left, not right. And this time our left will remain intact, and right will basically be index minus 1. And then finally we can just simply return root, and let's return DFS on our pre-order, post-order. They are accessible inside DFS, but we have to provide left and right pointer, which will be 0, and in order, post-order anything can be given over here. Let's give in order, and that's because they're of both same length, so -1 because we are dealing with the indexes here. So let me zoom out and try to run it. All right, let's try to submit it. Okay, let's write down the time complexity, which is time complexity is going to be big of n. That's the number of time we are visiting each node, and we already created this, so space complexity is going to be big of n as well. And this helped us to reduce time complexity from big of n square to big of n, because now while looking up the index, we can simply look it up in big of 1. Now space complexity is big of n. Okay, awesome. Let's go back to AlgoYogi and mark this done. Check this out, and please make use of AlgoYogi. We'll be adding 500 problems over here, and their solution you'll be able to find over here. This is not the updated one, but I will add. You can check this video out as well if you like. All right, see you guys in the next problem. Bye bye.